Okay, so we're back. I just want to go ahead and post the calculations that I have, the end result of the calculations that I did so that you can check. And so those are written in green here. You should end up with a final area of the snowflake of 4 root 3 over 5, which I think is absolutely beautiful that you can actually compute the area inside this infinite length curve. And let me just give you a hint. What you should be thinking about is that actually the geometric series here shows up. It's everything except that first term of A that you see. So what I've got here highlighted in purple is the part that you want to turn into a geometric series. And so I've done that here in green, and you'll want to go ahead and check your work with that. Check plugging that into the formulas for the sum of a geometric series, and show your work also for the area A of the equilateral triangle of length 1. And this is what you should get. Okay, so I want to do just two small examples to show you some more computations involving geometric series. And so I'll show you the Cantor-Ternary set, which is closely related to this Koch curve. And so it starts out as the Koch curve does. At stage 0 is just the unit line segment. And then stage 1, what we're going to do is remove the middle third. And so we're left with 2 line segments of each length 1/3, but we're not going to replace that removed segment with a little triangular piece as we did with the snowflake curve. Rather, we just leave it empty. And then again in stage 2, we remove the middle thirds of each of the 2 previous segments. And so what's left, we have 4 segments of length 1/9. So I'd like to just show you, you can model the total, so calculate the total length removed using geometric series. Okay, so I've already gone ahead and written down a table here that we'll use. Again, I had some problems recording, so we have some left over from the previous one. So the columns of my table are what stage we have, the number of segments at that stage, the length of each segment at that stage, and then to get to the next stage, what length am I removing from each of my segments, and how many segments am I removing, and what's the total length that I remove to get from the stage that I'm currently at to the next stage. So at stage 0, there's 1 segment of length 1. The length of each removed segment is going to be 1/3, and the number of segments removed is 1, and the total length remaining is going to be, the total length removed is 1/3. So at stage 1, there's 2 segments, and the length of each segment is 1/3. The length of each removed segment is, we're removing 1/3 of the length of each segment. So 1/3 times 1/3. The number of segments we're removing is, we're removing 1/3 of each segment that exists in this stage. So we'll be removing 2 segments, and the total length removed is, in this case, 2 times 1/3 squared. Okay. At the next stage, all right, so stage 2, right, now let me go ahead and I'll zoom in a little bit, right? So now I want to be removing 1/3 of each of these 4 segments here. So let me go ahead and I will put those in green. I'm going to be removing these little green bits here, right? So, okay. So the number of segments at stage 2 is going to be, there are 4 of them. So, so in fact, there are twice as many segments in stage 2 than there were in stage 1. So I'm just going to write this as 2 times 2. And you'll recognize again that this is kind of similar to our process when we were coming up with summation formulas for Riemann sums. We wanted to sometimes write things out so we could see the pattern. And so that's why I'm doing this in this way. The length of the segments here is 1/3 of the remaining segments, right, are 1/3 of the length in the previous stage. So 1/3 times 1/3. And actually that's the same as the length of the remaining segments, or of the removed segments from the in going from stage 1 to stage 2. Right? And so, okay, so the length of each removed segment is going to be 1/3 of the, so the green here that I've highlighted is 1/3 of the length of a stage 2 segment. So it's going to be 1/3 cubed. And the number of segments remaining is going to be, well, let's see how many segments will be remaining here. Oh, sorry, how many segments are removed? Is number of green segments. There's 4 of these, so 2 times 2, right? And in fact, we're removing 1 segment in the next stage for each segment that exists in the current stage. So these numbers will always be equal. And the total length removed then is 2 squared times 1/3 cubed, right? So let me go ahead and write out one more of these. In the third stage, we'll have number of segments should again double, right? So there should be 8. So we'll have 2 to the 3rd segments. The length of each one of those should be 1/3 cubed. So that's the length, same as the length of the green segments that were removed in the previous stage. The length of the the removed segments that will be removed from stage 3 to stage 4 is going to be 1/3 the length of the current segments. So we'll raise the power there to 4. The number of segments removed will be removing 1 segment from the middle of each of the existing segments. So those 2 numbers will be equal. And then we'll have 2 cubed times 1/3 to the 4th power. So in the kth stage, right, we will be removing 2 to the k segments. The length of each of the segments should be 1/3. Sorry, we will, in the kth stage, we will have 2 to the k segments. The length of each of those segments should be 1/3 to the kth power. And the length of the removed segments will be 1/3 to the k plus 1. And the length of the number of segments removed should be 2 to the k. And the total length removed should be, and now I'm just going to write this as 1/3 times 2/3 to the k. Okay, so the total length removed after k stages, or let's see, the total length removed and let's actually just sum up all of these in this table if we're just considering in the limit. The total length removed is just going to be 1/3 plus 2 times 1/3 squared plus dot 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 plus 1/3 times 2/3 to the k plus dot dot dot. Okay, and so here, notice that this is equal to, we can write this in summation notation as 1/3 times 2/3 to the k, and summing from k equals 0 to infinity. And so now we can use our geometric series formula. We notice that our r here is 2/3, and that's less than 1. So we can use that formula. So we have that the overall length removed is 1/3 divided by 1 minus 2/3, right? And so that's 1/3 divided by 1/3, so that's 1. So we've removed a length of 1. So what does that tell us? That tells us that the overall length of the Cantor set, which is the limiting object that you get the set of all the points that remains, is 0. So it has 0 length, but there's actually, you can prove that there's an uncountable number of these points. So that's something that you would study in a further course. In fact, in the course Foundations, if you end up continuing on in mathematics, so you can kind of quantify this set of points, and it turns out that there's a lot of points there, but yet their total length is 0. All right. As a final example, I'll just comment that you can do a similar thing. So we won't necessarily go through this, but I will provide an answer here, so you can, in a similar way, compute. So this will be your turn. Compute the area removed in the Sierpinski carpet. And that area should actually also be equal to 1. So remember that the Sierpinski carpet started with a square of side length 1, and so the overall area is 1. And so if you actually compute how much area you remove, what you end up seeing is that the area you remove is equal to 1. So in other words, the overall ending fractal has no area, even though there are a lot of points in that carpet. So so that'll be your turn. So I would like you to actually think about how you would do that and set up a table and show that you end up with an area of 1 there. For your assignment E, what I'd like you to do, and I hope this will be a fun activity for you, is use what we've talked about so far, and I know there's a lot of examples that we've covered here, but try to creatively come up with your own fractal in a similar, using a similar method to what we've used here, and describe in words what that iterative process is. And so you can do something like a Menger sponge with in 3 dimensions, or you can do something like we've talked about in 2 dimensions, and sketch a bunch of the stages in the construction. So I'm asking you for 4 stages. That will be the first, the initial stage 0 plus a 1, 2, and a 3, and then make a conjecture. If you have something that you've drawn in the plane, then make a conjecture about the perimeter and the area of your fractal, so length and area of your fractal, or area and volume if your fractal is living in higher dimensions, and then use a geometric series to compute at least one of those, perimeter, area, or volume of your fractal. So I'd like for you to do that, and that won't be due until next Wednesday, so a week from today. And please contact me if you have any questions. I'd be happy to talk with you. what I'd like to do is create a little class gallery of your fractals and let you see what each of you has produced. I think these could be really fun. And the other thing I will do for you is, it turns out these fractals are typically not objects that we would consider one-dimensional or two-dimensional, right? So like that Koch curve is a very wiggly line. So it's not really something that we would think of as being one-dimensional like a line, but it's not really two-dimensional, so it doesn't really take up any area. So it has some sort of a fractional dimension. And so whatever your fractal is, I'll go ahead and do the computation and let you know a few fun facts about the fractal that you create. So have fun. I hope you enjoy this, and definitely let me know as you progress if you have questions or just want to talk over your ideas for this. I'm thinking of this as kind of like a mini project, so nothing of like super giant weight, but something that hopefully you'll be able to be a little bit creative about and practice describing your construction in words. So, all right, enjoy.